And welcome to another edition of Terms Defined. This one is going to go through all kinds of different stuff. We're going to be talking about solar minimum, grand solar minimum, cosmic rays, and the galactic current sheet. And there certainly is one, although your beliefs about it might be a little bit off. But anyway, let's start talking about solar minimums. Solar minima are pretty interesting in that sort of the source of the solar cycles is not really understood. We don't really understand why it is that the sun behaves the way it does, what's really behind the 11-year cycles. It's part of the reason why we make our videos and why we spend so much time delving very deep into the sort of day-to-day activity of the sun. And, the difference between a solar minimum and a grand solar minimum. And there's a lot of stuff that goes into this. This stuff is all sort of related. And, that's part of the reason why we brought EUGENE on for this video, as he's fairly versed in the subject, plus he sort of knows a bit about what's going on at the subatomic level. Welcome, EUGENE.
Yeah, hello everyone. Hello, Daniel.
Cheers. Thanks for coming to another Terms Defined. 2 in a row. It's a double header today.
Yeah, but in the previous one you screwed up the video recording.
Yeah, sorry about that,
so
man.
I was... No, I'll never forgive you.
We're going to have a still image of EUGENE. We've got a still image of EUGENE with the river Styx there. Sorry about that, man.
You'll have to carry the burden to hell with you.
By the way, we've got Cygnus A behind my head on this one. That's the massive radio galaxy Cygnus A right there, right at that moment. There's Cygnus A back there. And so anyway, yeah. So let's talk about solar minimum versus grand solar minimum. What do you know about that, EUGENE? I'm sure you have some opinions on that sort of stuff.
Well, I would say that, I don't know the formal definition, but I guess people call grand solar minimum a very prolonged minimum, like let's say, which spans more than one cycle. So that's...
More than one cycle, sure exactly. More than one cycle.
I'm not sure if you can call it, say, Maunder minimum a grand solar minimum, or a Dalton minimum, which wasn't kind of a minimum at all. I mean, cycles were still there, they were just kind of weaker. But in Maunder minimum, we suspect there was no sunspots at all, right? But what people should remember, and I think it's not really emphasized as much as it should be, that we don't have actual records of the numbers of sunspots during Maunder minimum. We have only secondary accounts through which we conclude that there was a grand solar or something like a grand solar minimum during Maunder minimum, because sunspot records only appeared in the middle, like steady, counts of sunspots only started to appear in the middle of the 18th century, so that's 1750s. So that's basically 100 years later after the Maunder minimum. So that was solar cycle 1. I think it started in 1750 or something, or 55 maybe. So even Maunder minimum is basically, let's say, a concept which is not really proven by data, but we think it was there. So, I mean, you have to remember that at least. So if you're making some conclusions, sure. You have to remember that the Maunder minimum itself is not really 100% proven. That's what I'm saying. But anyway, I would guess that, yeah, you can call something like that a grand minimum when, let's say, for 30 or 40 years you have basically almost or at completely no sunspots, and therefore very low solar activity in general. Right. Something like that, I would guess.
Right. So, just to fast forward to now, how many do we have right now? Like 30. The radio flux is like 80 right now.
Yeah, I think to 2019 and even maybe 2020 were among the top years in terms of the number of days without sunspots.
Correct.
Mm-hmm.
And there's definitely a lot of people who are sitting around hoping that we have 0 sunspots as time goes on. And it doesn't necessarily pain me to report when there are some. But in any case, the point is, a grand solar minimum is multiple very low sunspot cycles in a row. So let's talk about some of the data points, right? And the first one I'd like to cite is the thermosphere index. If you look at the thermosphere index of the last solar minimum, it was drastically lower than it is now. And that's sort of one of the the thermosphere is sort of the outermost atmosphere, the thing that most directly interacts with solar radiation. You would expect it to be lower if you're going to have 2 really low solar minima in a row. But we see a much higher thermosphere index between cycle 24 and 25 than we did between cycle 23 and 24. Any thoughts?
That's interesting. Well, I don't know, really. I mean, as I'm not a specialist, but I think thermosphere reacts mostly to like UV and X-ray. I guess that's what
probably
really
I would think so
enhances it. So I'm not sure why do we have such a discrepancy. I mean, there's actually fairly recent studies that have claimed that during the solar minima, the gamma ray flux from the sun is greatly enhanced, and especially in like super high energy gamma rays. And somehow they're mostly emitted from equatorial area, and nobody knows why. Like, none of the mechanisms of the production of these gammas seem to explain, hypothetical mechanisms seem to explain this pattern, and it's still a big question.
Now that I'm not familiar with at all. I never heard of that mentioned whatsoever.
Mm-hmm. Well, there were preprints like a year plus ago, of these papers, and there was, I think it was like finally printed in a real, so to speak, journal very recently, like maybe a month ago or something.
Oh, geez.
But yeah, there's a
maybe we can link to that in the video or something. Maybe we can link to that. Maybe we can link to that article in the video or something.
Yeah.
That'd be great.
I'll give you some links. Yeah.
But
okay, so basically my point was that I'm not sure if sunspot activity is really necessary for, like this thermosphere and enhancement. Although, indeed, I would say that what you just said seems suspicious to me. Like, it's strange. I cannot really explain it. I mean, usually, indeed, you expect, and it's actually a technical problem. I mean, it's a thing that is taken into account by people who launch satellites because they need to know how quickly the orbit would decay.
Sure.
And you may have heard, and obviously during solar maximum, when the X-ray flux and UV flux is much higher, the atmosphere expands more, so there is a higher drag on the satellites in low Earth orbit, so the orbit decays faster, and much faster, actually. Like, you can launch a satellite during a minimum and it would stay in orbit without any corrections for like maybe 6 years, and you launch the same satellite to the same orbit during solar maximum, and it falls in like 2 years maybe.
I see what you mean.
There was a famous story about the Skylab station, the first American space station.
Yeah.
Where they didn't really take into account the high solar activity at that time, like late 70s, I think.
Oh, really?
And in the end, so they planned to launch a shuttle there to boost it up, to keep it in orbit. But they didn't take into account the higher solar activity. So the orbit decayed and the station fell, like, I think 4 years too early. So their planned mission was too late, basically. So they couldn't save the station in the end.
Right.
4 years, that's a lot of time, as you might imagine. So.
Yeah,
but also you have to take into account that the decay of the orbit is sort of like an exponential process. So it starts really slowly, but when it started, it just accelerates exponentially, because as you fall, you go into more and more dense layers of the atmosphere, and the orbit becomes
slower and slower speeds.
dense. Starts decaying quicker and quicker, basically. Yeah.
Friction increases, right?
Well, it's not really friction. I mean, we're talking about like Mach 22 speeds, so it's shock waves, really, not friction.
Well, 12,000, 16,000 miles an hour or something like that, right?
Well, 8 kilometers per second, let's say. I'm not sure how much is it per hour. I don't really see a point in describing such velocities in terms of kilometers per hour. It's just pointless.
Yeah, you're right. But the video is going to be on YouTube, so people want to know that, you know. Interestingly, I saw an article. It's been all over the science news. The clickbait title is "Supermassive Black Hole Headed Directly Toward the Earth." If you read about it, it's about how the Andromeda Galaxy is headed toward the Milky Way galaxy. You know, M31. So it's like,
yeah.
Oh noes, the supermassive black hole's headed toward the Earth at the core of the Andromeda Galaxy at 114 kilometers a second or whatever. It's utter clickbait. It's only been known about for decades that there's this trajectory apparently with M31. But in any case, which actually I guess brings me to another interesting topic, cosmic rays. So, you know, we talked a little bit about solar minimum. Of course, solar minimum maximum is also a reason why or why not to go to Mars, which is sort of a segue, I guess, to cosmic rays as well. You know, cosmic rays. So we've got, for the most part, it's about the same constituents as what you'd see out of the solar wind, but they're flying through space, sort of in their own direction in a lot of ways. And while the sun is sort of the primary source of cosmic rays, it's also interesting that we sort of seem to see some cosmic rays coming out of the planet too, such as in Antarctica. And I think that may be less surprising with condensed matter theories of things like stars and planets, but without going all into all of that sort of stuff, what do you have to say about cosmic rays? Because they're very important in terms of like climate, but they're also very important in terms of cosmology, because we want to know how they're generated and so on, and how they affect the interactions between celestial bodies, I guess I'll say.
Mm-hmm. Well, you've already mentioned like a ton of things that we can talk about. Like, firstly, you mentioned the possibility of, let's say, solar system exploration. And I remember a paper from 2014 or 15 where they've specifically studied the lowering of the solar activity in recent decades, let's say, and the possibility, I mean, if you project that further linearly, let's say, and you assume that the next cycle would be even weaker, etc., that would mean that there would be more cosmic rays, because, you know, the Forbush decrease process, where basically the solar plasma kind of sweeps out cosmic rays from the system, right?
It makes it more likely for them to react with something and do something besides be on the same path they used to be on, instead of continuing on as a cosmic ray, right?
So basically there is and it's a sort of a very well-known fact, or at least it is assumed always, that the solar activity inversely correlates to cosmic ray flux. So the more active the sun is, the less there is cosmic rays, essentially.
It is assumed,
so
yes.
What they studied in this paper was the possibility of space flight, I mean, like beyond low Earth orbit, in such a circumstance if the solar activity continues to drop, as it does currently, or at least seems to. And they've, let's say, the conclusions was that the cosmic ray flux would become so high that this, let's say, the trip to Mars would be much less safe,
fatal,
than it was previously.
It would be fatal now, you know, if the conditions were...
Well, I mean, they're talking in terms of risks, like risks to get cancer, etc., which is on its own, like, you can deconstruct this very concept, etc.
Maybe.
But let's say that way or another, any negative effects of cosmic rays that you may have on your body would be enhanced during the next cycles if the sun continues to weaken. Right? So if you look at the 60s, like the space age era, 60s and 70s, where people started going into space, the solar activity was much, much higher than it is currently. It was actually like the peak of the modern maximum, what is called, like, you know, the second half of the 20th century, where when the sun was, some studies say, the most active in the last couple of thousands of years.
Around 1958 or so, yeah, like 1958,
yes,
59.
Something like that, like after World War II, basically, something like that. So, and currently, again,
yeah,
the
hottest thermosphere, the hottest thermosphere and the most sunspots and the highest radio flux that we've ever seen, late 50s, for sure.
Mm-hmm. One other interesting thing was that during 60s there was a lot of nuclear testing, like high altitude explosions, and they actually contributed a lot of charged particles. I mean, if you look at the explosion of a nuclear bomb or even thermonuclear bomb, it releases a ton of charged particles, right?
Especially when done in
those
space.
Those particles were trapped in the magnetosphere of Earth, and Van Allen belts, because of that, were much thicker in the 60s and the 70s. And actually, like, some of these explosions, like in early 60s, there were basically only a few satellites around Earth, like maybe 5 or 7. And one of these explosions, the Starfish Prime, at the altitude of 400 kilometers, I think, or 600, it actually killed a couple of satellites just because it released so many of these new high-energy particles that the satellite crossed the orbits of these new particles in the magnetosphere, and it died because of that, which is kind of interesting. And as I've claimed multiple times, that this is one interesting argument in favor of, you know, lunar hoax idea, you know, which I not necessarily support, but still I acknowledge that such an idea has the right to be out there. Indeed, Van Allen belts in like 1969 were much thicker than they are today. So they would be much more dangerous than they are today to humans to traverse. But anyway, that was only one topic with regards to spaceflight. But in general, I actually want to mention one interesting hypothesis. Like, we assume currently that cosmic rays come from like galactic sources, like supernovae or whatever. Like, somehow galaxy generates these charged particles, mostly protons, by the way.
I think
it's
all
like
stars,
95%.
All stars generate them, I'd say.
Maybe, but anyway. So, and that's another interesting thing to consider, is that 95 or about % of the cosmic rays are protons, and the rest is electrons. So they are actually charged. Positively charged. Like they have net positive charge.
They're dragging electrons along with them, I think. Or
no, you see, the thing is, you have to look at the mechanism, how they are deflected by the interplanetary magnetic field emitted by the sun or produced by the sun. So the thing is that in a magnetic field, charged particles start rotating around the magnetic field vector, right? And the more massive the particle is, the less is this radius of rotation.
Okay.
Right? Just because of inertia, right? So very light particles have
essentially that's Markland convection right there, essentially.
No, that's not Markland convection. I told you before that Markland convection is caused by E cross B drift, which is a drift. It's not just a rotation.
Okay, anyway, go back to what you were saying. I apologize.
I was saying that electrons have these gyro radii, as they are called, around the magnetic field, much larger, which means that they are being deflected stronger by the solar magnetic field. So there is much less electrons in the cosmic rays that get into the solar system, because most of them are getting, their trajectories are getting deflected so much that they don't get into the solar system.
The sun is going to have a thing like a Van Allen belt, like the Earth has a thing like a Van Allen belt. So things that are attempting to enter the heliosphere, they have to do it via charge aligned currents, the same way they got to do it to enter the Earth's magnetosphere, we would assume. So this is part of the reason why we would think that the solar heliosphere,
because
we would think the solar heliosphere is crescent shaped.
The heliosphere has the solar wind, whereas on Earth we don't have an Earth wind. So the shape of the let's say plasmasphere, tentatively around the sun, is completely different with respect to the
right. That's why I was saying
plasma is in the Earth's magnetosphere.
That's why I was saying it's probably shaped like a croissant. In other words,
no, it's probably not even there in the first place. That's what I'm saying. There is a plasma torus around the sun. Yes, that is indeed the case, and it is caused by, again, the shape of the magnetic field of the sun itself in the first place. But anyway, the point I was trying to make is that only high energy protons can reach the solar system in the first place, because, again, the higher the energy is, the less is this gyro radius. So electrons, most of them get lost along the way because they have larger gyro radius, so they're swept out by the magnetic field of the heliosphere. The protons, only some of them can get in, and those are the protons with a higher energy, like 10 giga-electron volts.
I would tend to
roughly,
agree.
I think. Because if you have a proton with a lesser energy, then it would be swept out again, because its gyro radius would be of the order of the size of the heliosphere itself, so 100 AU roughly, or something. So it would, as it would enter the heliosphere, and its trajectory would be curved so much that it would just go outside again.
Right.
So that's the point. That's why only higher energy particles can enter.
Right.
And I would assume that the electrons that we have even higher energy, again, due to lower mass. They need to have higher energy to
Let me just interrupt you there. And this is part of the reason why we have so few known cosmic ray flux point sources, because of exactly what you were just saying. In other words, so when we look at an object out there and we see that its X-ray flux coincides with cosmic ray flux from a ground-based neutron detector, I would say that's probably kind of important to overall cosmology stuff. Wouldn't you tend to agree?
I haven't finished my thought, so that was only like a preface to the hypothesis I wanted to.
No, by all means, continue.
I became distracted by my own thoughts. But anyway,
distract away.
I was talking about the sources of the cosmic rays, and I said that we assume that they come from the galaxy, like on large scale, let's say. But Alfvén, in one of his books, or maybe even more than one, I think in Cosmic Plasma, he talks about the possibility that the cosmic rays are actually generated by the heliosphere itself. And that's a very interesting idea, in my opinion. Like, he said, because, again,
I understand
the flux of the cosmic rays in general is roughly homogeneous, so we receive isotropic, I should have said, because we receive more or less the same flux from everywhere in the sky, right? So Alfvén said, well, maybe it's the heliosphere itself that generates this flux.
We don't receive.
That's why
we don't receive nearly the same. We do not receive nearly the same flux from everywhere in the sky.
Yes, we do. Only when we're talking about very high energy cosmic rays, like electron volts, then we see a strong inhomogeneity. Like, indeed, there you can point to areas which have a much higher flux than other areas, etc. But if you look at all the population, especially low energy ones, like 10, 20 giga-electron volts, they're nearly homogeneous. Like, with a very good, precision, like maybe 0.1% difference here and there, but Other than that, they're coming from all the directions in the same amount. So, and Alfvén had an idea, well, maybe the heliosphere itself somehow accelerates these particles, but I'm not sure how it coincides, how it aligns with Voyager data. Like, I'm not sure if Voyager actually measures cosmic rays in the first place, but that would be an interesting thing to look into. Like, because we assume currently that Voyagers have exited the heliosphere, right?
I don't know. I don't think entirely. I would imagine it would enter into some sort of a plasmasphere. So if it's where it thinks it is, it should have crossed into some sort of a barrier, which would be like equivalent to moving through one of the Earth Van Allen belts, perhaps, into an area. Maybe it's the heliospheric plasmasphere. It's very hard to say,
Yeah,
sir.
well,
And there's a lot of
well, this
conjecture as to
certainly.
how the heliosphere is shaped. So, like you were saying before, it's certainly not shaped. I mean, I would not assume that it's shaped the same way that the Earth's uh, magnetosphere is shaped. But it's still probably.
Actually, nobody knows today
Well,
how
of
it's
course,
shaped.
no,
Like
nobody knows because we only have two
there are at
things.
least
There is a bit of a
so
delay. I apologize, folks, and Eugene. There's a bit of a delay. Go on.
yeah, there's at least three different models of how the heliosphere is shaped, and nobody really knows which one is correct. Like there is a
Right.
model that it's basically a quasi-cometary shape, like it's basically kind of like a sphere with a long tail, where the tail is produced by what you can tentatively call a pressure from the interstellar winds, right? That's one model.
I would
The
agree.
second model states that it's actually much more spherical, so it doesn't have such a tail. Maybe it's slightly like bulged, but it's still more or less a sphere. And the third model is that it's kind of like, again, a croissant type of shape. So you have roughly a sphere and two kind of horns like up and down. Again,
Yeah. And
kind of
this is the one that
I
I.
actually showed it incorrect. Like they should be curved in the same direction.
Yeah, yeah, yeah.
So, and this it is produced by the fast solar winds from coronal holes. These two horns, two curved tubes, basically. So,
Right,
and nobody
because
knows to this day which model is correct. So,
right.
yeah, they
However,
all agree with the data that we have. Unfortunately, we don't have much data, so that's the problem.
yeah, and all stars seem to have poloidal field-based coronal holes that emit more X-rays and more cosmic rays than any other part of the star. So there are poloidal
I would
fields
actually disagree.
on the sun, and there are poloidal fields apparently on every star. Since when you're viewing a star from its poloid, same way when you're viewing a galaxy from its poloid, which is what makes it a blazar or for a Seyfert 2 galaxy or a Seyfert 1 galaxy or whatever. It all has to do with perspective. Because if you look at the sun from the poles, it looks like a donut, not like a sphere. And that's because it has enduring coronal holes at the poles. You disagree?
Yeah, but you said that the flux of X-rays is higher in coronal holes, which I would disagree with. I would say it's actually lower because, like, it is assumed that the temperature of plasma is lower at coronal holes and
Oh,
the
I see what you're
density of
saying.
plasma is lower.
Well, I mean, you can certainly say that cosmic ray flux would be higher. So, it's super obvious that when we view galaxies down their poloidal fields, that we see much more X-rays from them. And
Maybe, but I'm not sure. I think actually most of the flux of the sun in terms of X-rays comes from the equatorial regions. That would
I
be
don't
my
think it's
statement. And
I don't think it's any sort of a debate. The reason that we look at Seyfert 2 and Seyfert 1 and blazars and quasars is because they're the brightest objects in the universe. The reason they're so bright is because you're looking down their poloidal fields. Those fields seem to, for some reason, accelerate everything. Whether it's cosmic rays or it's only photons, can be up for debate. But these objects clearly emit the most X-rays of anything that we're seeing. When you're seeing a gamma ray object. In other words, Cygnus A, this galaxy that's behind my head right now, that's a radio galaxy. We don't see a high X-ray flux out of it. We see a high radio flux out of it.
Well, I can envision, let's say, mechanisms how you can generate X-rays in, like, let's say, through other means than just the like emission by the surface, so to speak, itself. So maybe you might claim that, okay, we have charged particles that move along these magnetic field lines, let's say, above the coronal hole, which are assumed to be, just streaming outwards like open magnetic field lines, and
Okay.
these particles may, through some other mechanisms, accelerate along this magnetic field line, and then they would emit these X-rays and whatnot. But on the sun, and then again, looking like down the barrel, so to speak, you would see higher X-ray flux because of that. But on the sun, we actually see higher X-ray flux and higher extreme UV light from the equatorial regions. Again, look at the SDO images, like in 131 angstroms. You would see that coronal holes are darker than the regular, so to speak, sun, which means that the flux of extreme UV is lower from the coronal holes. Well, that's kind of obvious, I think.
Sunspots move toward the equator toward the end of solar cycles, and they only exist at a certain latitude between the poles and the equator. So yes, you're going to have a higher X-ray flux on the surface. I mean, toward the equator over time, because over the solar cycles, sunspots move toward the equator. But you're talking about photons versus protons here. Once again, cosmic rays isn't solar flaring and X-ray flux. It's a completely different. It's photons versus protons. So.
Yeah, but anyway,
at the poles,
photons are emitted by protons. So where you have a higher energy protons, you would have higher energy photons emitted by them. And the reason why we have higher energy protons emitted from the equatorial region is, again, the shape of the magnetic fields of the sun, which is, if you envision them as a simple magnetic dipole as we have on Earth, which would be like a first approximation to what we have on the sun during solar minimum.
But it's two dipoles. It's two dipoles.
Kind of, but in the first approximation, we might just assume that it's a single dipole. So,
but we shouldn't assume that, because it isn't that. It's two dipoles. If you want to break it down to that level, how are you going to say it's like a bar magnet? You're essentially saying it's like a bar magnet.
Yes, that's what I'm essentially
saying.
But
it isn't like the bar
magnet. Minimum, it's very much like a bar magnet, except that you have also this streamer belt in the equatorial region, which
it's not like a bar
allow
magnet.
The field lines from the north and the south to connect, but rather kind of makes them produce the current sheet that we have.
You've got a north and a south pole in the north, and a north and a south pole in the south, and the interaction of those two fields is the B field. That's
no,
yeah.
That's not how it works, man.
All right. Well, I don't know what to tell you, but it couldn't possibly work as a bar magnet, because it's all these diagrams of the Earth and the sun as a bar magnet.
It has a north coronal hole with north magnetic polarity, so the magnetic field sticks out of the sun in the north, and it enters the sun in the south because you have a southern magnetic polarity coronal hole there. That's what you have, and it's basically a bar magnet, again, except the equatorial area, which does not allow, due to the solar winds again, for these two fields to combine. So they kind of, let's say in the north, the field exits the sun, and then it kind of goes outwards in the equator. There's this outgoing plasma.
There's a push me pull you going on depending on which pole you're associated with. Yes, I would agree with you on that. There's a push me pull you situation. In other words, one polarity versus the other.
That you have two dipoles, it would mean that you would have 4 coronal holes instead of 2. So you'd have one, let's say, not north polarity in the north and one south polarity in the north. And the same for the south, which we don't see. Like we see only two coronal poles essentially. But during the solar maxima, yeah, they kind of migrate from the poles to the equator, and they kind of mix in weird ways, and then they kind of continue their motion and switch places for the next minimum. Right? So in this minimum, we have north magnetic polarity in the north and south in the south. In the next minimum, it would be vice versa. So north would migrate to the south. And
No, sunspots are almost entirely on the equator at the minimum. When you see the next cycle happen, you see sunspots closer to the poles. At the minimum, you see sunspots at the equator.
So that doesn't contradict
throughout the cycle. Throughout the cycle, at solar minimum, you only see sunspots at the equator. That's part of the way you know that it's a minimum. At the beginning of a cycle, you see them at very high latitudes.
Yes, at minimum they're at high latitudes. Indeed.
But at maximum, they're only at the equator.
Well, almost, like maybe 5 degrees latitude or something.
Okay. Anyway, let's just move on to this, because we're going to clearly disagree on certain aspects of this, and we certainly should. Let's talk about the quote galactic current sheet, because this is one that I've been just dying to talk to people and actually put out a video about it, because I'm so sick of hearing about it. And in terms of the sun reacting to a galactic current sheet, I don't think that's got anything to do with anything. Sagittarius A star, although the sun orbits the core of the Milky Way galaxy, known as Sagittarius A star, Sagittarius A star is not putting out a stellar wind like in the context of, the sun's heliosphere behaves like the Earth's fractally compared to the way Sagittarius A star is putting out a stellar wind. I think that's a ridiculous idea. And just the idea that the galactic wind is Sagittarius A star's direct output and all this, and that's creating some kind of galactic current sheet that controls the catastrophe cycle, is just a joke. What say you? I'm sure our viewers are aware of what I'm talking about here.
Yes, I would agree that the idea is a joke, but I would disagree that Sagittarius A doesn't emit stellar winds. It certainly does.
No, it does. It does, but they're not like interacting with the sun the way the sun's interacting with the Earth. That's what I'm saying. It certainly has a stellar wind, but it's not like we're not in it. We're not living in its stellar wind. It's the core of the galaxies is complicated as hell, and it's not anything like the sun versus the Earth. That's what I'm saying.
Yes, absolutely. And that was one of the arguments I made in my email discussion, if you may call it that, with Ben Davidson.
Yeah, thank you. And thank you for doing so, because it's such a ridiculous notion that it pisses me off. And, I'm glad that somebody has a brain about it.
I think we should add the link to the whole discussion, which I've screenshotted.
Yes, by all means. Whatever you want to put in, man.
I didn't make it.
I won't censor you.
I didn't put it as a text because he decided to use colors, so I had to actually screenshot the whole discussion.
He decided to use colors. Did you say?
Yes.
What is he in a gang like the Crips and the Bloods or something? What colors? What do you mean he was using colors?
Yeah, he used, I think, red color for his replies, like under my text. He just copied my text.
Okay.
But anyway, so the point I was making there is that the difference, let's say, well, I didn't actually make this point. I thought it was kind of self-evident, but I probably should have made this point. That
by all
the difference
means.
between, let's say, the interplanetary magnetic field and galactic magnetic field, like when he draws this analogy that the Earth crosses the solar current sheet every week or 2 weeks, it doesn't really matter, but
different amounts of time,
even though the Earth's orbit is 1 year long, right? So it's much faster. And he says that then the stellar sun's orbit around the galaxy is 250 million years or so, but it also should cross the galactic current sheet much more frequently, right? because there's a clear analogy. Well, whereas my point was, no, there's no clear analogy because the Earth is not a plasma thing, whereas the sun and all the structures around it are made of plasma, and therefore they are affected by magnetic fields, which permeate like everything around us. So if we don't see any signs of a current sheet around us in all those plasma structures, like local interstellar cloud, local interstellar chimney, which is like 1,000 parsecs wide, etc. So if there was a current sheet, it would be apparent in these structures too. You see?
And
if there was a current sheet
let me just slow
around
you
us
down.
anywhere
Let me
near us.
slow you down a minute because some of our viewers might be cosmology noobs here. When he's talking about he's talking about the local cluster here now. So Eugene is not galaxies. He's talking about the local the local stellar situation. So he's talking about the local chimney.
Yes.
Can you just like give a little bit of description of like what the local chimney is? The way the
Yeah.
sun appears to be moving with respect to relative motion and stuff within the galaxy might not be as simple as just an orbit around the core of the galaxy, right?
Yeah, so basically, the sun and its closest stars, let's say maybe 100 or 1,000 of them, they are basically in the same region of galaxy, right? So they're orbiting the galaxy in the same way. And that's what is called the local rest frame, where like you take this moving frame of reference as a basis, right? You attach your frame of reference to it. But in this rest frame, there's also relative motions of stars with respect to each other, much smaller with respect to their motion around the galaxy, which is very fast. But these motions are like maybe a few kilometers per second, whereas around the galaxy we're moving with a velocity of 255. So that's basically like 100 times smaller type of motion. But it is still there. And there's plenty of plasma structures and gaseous clouds, molecular clouds around Earth, around the solar system, of the size of, let's say, 10 light years or maybe 30 light years. So there is what is called the local interstellar cloud, which is, again, this plasma cloud around the solar system, or at least somewhere nearby, where we are going, which we are entering or exiting or whatever. So there's plenty of all these structures, and maybe, again, we should post a link to some of the pictures. That's one scale, right? Around 30 light years, let's say.
Yeah, I wish somebody had a really good animation of this. Like a sort of an animation, like a zoom in, zoom out thing, where you could show people sort of how the stars are moving and super exaggerate their motions or something. I'm sure somebody's probably made some sort of an animation like this before, but it might help people to sort of.
It actually pains me to say this, but I was working on such animation with a collective of other people. But unfortunately, these other people became involved in other projects and basically stopped working on this. But it's called, it was an idea, a great idea, in my opinion, to visualize all of that. And we have like a pre-alpha version of our thing actually still up, I think, and I'll send you the link.
I think I've seen it.
Plasmascape.
I've seen it. Yeah, I've seen it. I found it without. Nobody ever sent me a link to it or anything, and I've talked to some of the people that were involved in the making of it. But
yeah,
okay,
well,
cool. I was wondering if
in the making of it, like
you're still credited. Yeah, I'm pretty sure you're still credited. So that's cool. Yeah, Plasmascape. Yeah.
My role was basically Python programming of the correct orbits and correct alignments and correct reference frame, like rotations, etc. So and I've exported it to Blender, and then other people used like David Johnson was one of them who used Blender, my Blender product, let's say, to integrate it into Verge, and from there into the HTML on the website. So it was kind of a long pipeline, and I can only manage the first part of it. I cannot really work with the Verge, etc. So that's why the project stopped, because, well, roughly speaking, David stopped working on it, unfortunately, but it was a cool idea. But anyway, so there's this one scale of roughly tens of light years, right? And there's plenty of plasma structures there, where, again, magnetic fields are heavily connected to the plasma they're moving along with. And there is a larger scale of, let's say, hundreds of parsecs, like hundreds of light years. Parsec is 3.2 light years, I think. But anyway, so in this scale, there is this other structure called local chimney, local interstellar chimney, which is basically, roughly speaking, a kind of an hourglass-shaped cavity, roughly perpendicular to the galactic plane. So its walls are made of plasma, roughly speaking, but inside of it, there is less plasma density, or at least less density of some specific species, like, I think, neutral hydrogen or ionized hydrogen or something.
Sure,
like
that would make sense.
And that's why, by the way, and extragalactic astronomers know this very well, we have what is called Lochman Hole, which is like this opening of this hourglass shape, where, like, if you look roughly perpendicular to the galactic plane, you see a much clearer area. So there's less hydrogen blocking your view. And that's why extragalactic astronomy benefits from this structure, because, well, the walls aren't there, if you look up or down along the axis of this hourglass. So you can see farther into the universe, because there's less stuff along the way,
Right.
There's stuff is concentrated in these walls. So this thing is like, its width is roughly, I would say, maybe 500 light years or something like that. But the structure is there, and you see no current sheets crossing it anywhere. Like, it's not disrupted by
I see what you're saying.
Such thingies. So this is my argument, at least one of, in favor of the idea that we're not crossing any current sheet anytime soon, and we probably haven't for, again, hundreds of thousands of years at the very least. I would say millions of years at the very least.
I see.
Because galactic magnetic field, which is the reason for the existence of the galactic current sheet, is connected to the galactic plasma. And we don't see any evidence of such a current sheet in these plasma structures of a large scale. Again, like, let's say 600 light years. It's not very soon that the plasma would traverse such a distance,
I would say it's connected. It's connected to the galactic plasma in that the plasma aligns to the magnetic fields.
Yes, that's exactly what I'm saying.
This is the problem that I have with a lot of people when they freaking think that plasma is magic. The plasma is aligning to the magnetic fields and telling us where they are. Plasma doesn't become magnetic. It doesn't become the magnet. In other words, it heats up, gets moved around, and so on by the magnetic fields. It isn't the magnetic fields. It elicits where the magnetic fields are located.
Yeah. Well, that's, again, speaking about Alfvén, that's one approach, to look at the magnetic fields, which is kind of useful a lot of the time, but there's another side of the issue where you talk about electric currents.
Because yes.
Basically, magnetic fields and electric currents are interchangeable, because one creates another and the other creates, the former. So the reason we're talking about, let's say, solar magnetic field instead of solar current or whatever, is because we don't know what kind of current produces the solar magnetic field. We just don't see it. I mean, it's hidden somewhere inside the sun, apparently. So that's why it's much more useful to talk about the solar magnetic field. And the same is true for Earth, by the way. We cannot look inside the Earth to figure out what kind of currents produce its magnetic field. But we can operate with magnetic field just as well. I mean,
right,
and it's interchangeable.
I didn't.
But,
no, go on.
But in many astrophysical situations, again, as Alfvén had shown, it's much more productive to speak about electric currents instead of magnetic fields. And let's say, again, processes like magnetic storms or like particle acceleration in double layers and stuff, it's much more useful to consider it as an actual current, like circuit type of situations, rather than, this idiotic magnetic reconnection processes, etc. So if you just draw a circuit, it would be clear what exactly accelerates the current, what exactly produces, let's say, the dissipation of magnetic energy, etc. Whereas if you talk about magnetic reconnection, that's actually kind of magic type of situation where you just, by hand waving, you're just saying that the energy releases from out of nowhere just because the magnetic field lines snap. Whereas, well, it's just basically a bad idea.
Well, look, in any case, I didn't interrupt you when you said stars are made of plasma, and there's a reason for it. It's because this video is about a specific thing, and I don't want to get into I don't want to get even deeper into the weeds about talking about things like electron availability, why sunspots are dark, and why it's likely that stars are made of condensed matter, and what's going on the surface is the plasma. But in any case, anything else about solar minimum, cosmic rays, and the galactic current sheet? I think we've definitely created enough sound bites and enough whatever material to enrage lots of people that we regularly argue with online anyway. So
well, one thing I definitely wanted to mention is that firstly, galactic sheet seems to exist.
I would say it exists.
It's a thing.
I would think it's a thing.
It seems to be the thing.
Yeah.
But we don't really know how exactly the galactic magnetic field is shaped.
Yep. It's certainly at an angle. It's at an angle. It's not. If you look at the disc, if you look at the disc like this, it's not like at a 90-degree angle to the disc. It's like at a very like acute angle. There's the poles of the galaxy are not currently perpendicular to the Milky Way galaxy's disk. They're offset by a lot. And to complicate matters a hell of a lot more, there are some extremely tidally active objects around it, like S1 and S2 and all these stars that are blue supergiants, and they're orbiting the galactic core like 12 years, some of the closer ones. And they're incredibly elliptical orbits. The eccentricity is like 0.86 or something. So it's a lot more complicated. It would be equivalent to if you had the sun with 15 other stars orbiting around it. Anyway, the point is, what the activity that's going on in there is nothing like what the output of the sun is and the heliosphere is like. And I'm pretty sure that if Sagittarius A star suddenly turns on or something like that, if it's going to interact with our local environment, it needs to do so via the spiral arms of the galaxy, not via all the empty space blocked by a ton of dust between us and Sagittarius A star. That's the beef I have with the whole galactic wave theory, that Sagittarius A star is doing a giant nova event every certain period of time, and that's just constantly flying through space, and it's going to get you eventually. I don't think that's what's going on, and it's because of the complexity of that sort of system there at the core.
Yeah, some idiots like this Douglas Vogt even claim that every star actually goes nova every 12,000 years, which is kind of
it's a convenient theory. It's a convenient theory to explain a lot of stuff that's otherwise magically unexplainable. But what's the physics behind it? It's magic. It must be magic. You know what I mean?
Yes.
How can you have physics to explain that?
Anyway, I wanted to finish my statement with regards to current sheet. So firstly, it seems like it should exist. Secondly, we don't know the shape of it, not even nearly. There are at least two competing models currently of the galactic magnetic field, and we don't know which one is correct. And again, in my email exchange with Ben Davidson, I mentioned that, but he kind of just ignored that.
Well, why don't you email him like a man
I was
instead of?
asking him, like, what do you think the galactic magnetic field looks like? Like, why do you think that the current sheet is here currently, or whatever?
Yeah.
Because you see, not only do we have, and I've had an impression from what you said that you think that it's Sagittarius A, like single-handedly, so to speak, generates the galactic magnetic field, and I would strongly disagree. I think it's actually generated in a much more complex manner, and it's a result.
No.
Or rather,
did you quote me as saying Sagittarius A single-handedly generates the field? I don't think it's.
Well, you've claimed that, let's say, tidal effects from orbiting stars somehow change the magnetic field of the galaxy, whereas this is not the case, I would say. I mean, the galactic magnetic field is a characteristic of a whole galaxy. It's not just one object in the center that's responsible for it. That's what I'm saying.
Right. Isn't that essentially what I was saying?
There's a whole bunch of plasma and electric currents flowing here and there. And
Sure.
again, we don't know for sure yet how it is shaped in the first place, the magnetic field. Like, again, there are at least two viable models to describe what we're observing. And one other factor you cannot ignore is that we have spiral arms in the galaxy, which are associated with their own magnetic fields. So, and we are in one of these spiral arms, therefore, we don't just observe, roughly speaking, a dipolar component, from up to down.
Yeah, it's millions and millions of stars with their own sets of heliospheres that are in all different orientations.
Yes, and they're all involved in the production of the magnetic field, as well as like, I don't know, 10 to I don't know which power tons of plasma in between stars.
Yeah.
Which also carries a lot of current, etc., etc.
Absolutely.
So Alfvén had this basic model of the galactic circuit, where you have, let's say, outwards current through the plane of the galaxy, which then connects near the axis of the galaxy and goes inwards, or vice versa. It doesn't really matter.
Probably both directions at both ends, I would think, but in any case.
That was the model in like the first or even zeroth approximation of it, because you assume that the galaxy is a homogeneous disk here, whereas it's not. I mean, it has spiral arms and spaces in between them. So it's very, very, very complicated. And to claim that if you, let's say, just think about it on a very removed and abstract level. If you are in a one of these spiral arms, which we are, for example, do you think there is a current sheet crossing you? I would say probably not. I mean, probably you're actually in an area with a roughly homogeneous magnetic field. I mean, otherwise, why would the spiral arms be there in the first place if there's a current sheet constantly, flowing through them? That just seems idiotic.
That's a good point. Yeah, I never really thought of it that way, but yeah, that's a good point. And a lot of the, for instance, what would happen if we took the sun and we put it inside of an opaque box where it's not exposed to any magnetic fields, and it's not exposed to any other external stimulus of any kind, and you've got a camera inside the box that sends you a signal of what's going on. What does it do? Does the sun slowly burn out? What exactly happens in there? And of course, I'm not trying to put you on the spot, but this sort of figures into where we're going with all of this stuff. But we should close out the video. We're just about approaching an hour here, and I think it's pretty good timing. Perhaps we've gotten some wheels turning in some brains. Yeah.
Yeah, maybe. Well, I don't have an answer to your question because, well, firstly, it's an impossible situation, right? So nothing like that can possibly exist. So it's already kind of flawed. I mean, thought experiments are kind of cool, but on the other hand, they're really not. I mean, they don't correspond to anything in reality. So, but yeah, really, I have no answer because I don't know how stars work. So I have no answer to that. Like, I have serious doubts about the current models of stellar evolution, let's say, and things like that. So, I don't know, basically.
Yeah,
But
I would agree
I'm fairly convinced that we haven't had any solar nova, micronova, nanonova, femtonova events in the last, let's say,
whatever size
100,000
nova.
years.
Yeah, I hear you.
I mean, there probably were like very strong solar eruptions and very strong solar storms, but it's nothing like that would, turn the Earth upside down or whatever, that kind of stuff. No. I mean, one other argument I made to Ben Davidson, and he kind of freaked out because he probably never thought about it, was that if you have like such a huge explosion that basically, kind of sanitizes the whole planet, or at least a large chunk of it, causes huge tsunamis and whatnot. Like, what amount of species do you expect to survive? Like, if you say that, and I made an explicit calculation there, and I think, I mean, per 12K years, right? So if, let's say, 1% of species disappears or something like that, each event per 12,000 years, species would not be able to, speciate in that time frame. Like, in 1 million years,
it's
the
an
planet
important
would
point.
become barren. Only like super small bacteria, which doesn't care about anything at all, would survive. So yeah.
Yeah, and also this is one of the exact same kind of complaints that I have about electric stars. Because if stars were electric, they would be extremely unstable. I have a feeling that they're made out of condensed matter, but we got to save that for another video.
Yeah, actually, I mean, I've looked into this Robitaille's theory, and it looks pretty solid. No pun intended.
Awfully plausible.
I mean,
awfully plausible.
It looks liquid metallic. I would
the way that it rewrites all of cosmology is very interesting too. In fact, if that's really what's going on, or if it becomes a viable theory in the mainstream, it's going to create great jobs for people like you, sir.
Yeah, by the way, I may be fired very soon, like next week maybe, because I've supported the strike.
Well, I'll try to import you to the U.S. if you can get funded to get here. I'll like put my name on the dotted line. We can't be married, but we'll figure something out. I'll have a non-mail order Belarusian bride. I mean, a non-Russian. No, you got to go to France or Italy, right? That's your thing, right? France or Italy.
Well, again, I don't want to live there. I would be happy to stay there for like half a year.
I see.
But then come back. I mean, I love my country. I mean, it's just a country for me.
Well,
I don't really want to live anywhere else.
If there's anything I can do to keep you out of the gulag, I'll definitely do so. We got to close this video out though.
Yeah.
So yeah, that everybody make sure you subscribe to Eugene's channel, Eugene the Philosopher, and to look for more content coming soon like this. This has been another episode of Terms Defined. I've been your host, Dan, a.k.a. smAsho. Thanks again, Eugene.
Yeah, thank you for inviting me, and thanks to everyone watching this.
All right, great discussion.
Goodbye.
Talk to you soon.